Hi guys, welcome to another Learn Electronics Repair video. This was sent to me by a subscriber, Michael, and yeah, from Delaware, USA. Asked me if I could repair this. I think this might be quite interesting actually. I don't quite recall what he said was wrong with it. Maybe he's put a letter in with it. Otherwise I'll have to go find the emails. Took a little while to get here. I think I know exactly what this is going to be and why he wants it repairing. So let's have a look. Sapphire RX480 Nitro 8 gig. Okay, that's interesting. And we have a letter. Let me just check there's no personal information on this first. Okay, just yeah, we'll just take his email address, keep this private obviously, and his address. Okay, so this is what he says. Enclosed a Sapphire RX Nitro 488 gig VRAM edition. The card is not recognised in any PC slots anymore. They were used for gaming and mining. I noticed after removing the cooler that the VRM cooling pads had leaked some oily substance. This is quite common, especially when they've been used for mining. Since you're the expert, I'm hoping it can be fixed. I did not use a multimeter for testing it myself. Let me know how to proceed with payment and how, since I commonly use USD PayPal as fiat. Okay. Thank you for your time, and I must say, watching your work on YouTube, it's a privilege working with you. Oh, that's nice. So it's not detected by the PC. Let's have a look to see what's in the box. This is the sort of fault I like actually. I mean, the ones that drive me insane are like the ones where it crashes when the driver loads and this sort of nonsense going on. This is like, you know, what I call a proper fault. Yeah. So here's the graphics card. Sapphire Nitro looks quite nice. RX480. I think I have something similar to this here as well from somebody else, so maybe we can look at two together. Yep, that's exactly what it is. Okay, so let's see what we can do with this one. Yes, in fact I do have another one of these here. I thought it looked familiar. So this is the one that Alberto and Lewis asked me to repair. This is the subject of another video. I'll link it from this one. I've ordered this part, but I'm not sure it's actually faulty. And this has unusually low resistance on the 3.3 volt supply coming in from the PCIe. So I think it's a very good opportunity here that we might actually be able to get further with this one, even though the parts haven't arrived yet. And I don't, by the way, mean by taking parts from this one. But by making some comparisons, we might actually get a bit further with this as well. The first thing I'll just note, and this is the backing plate off Alberto and Lewis's card, is that they're not exactly identical, but they're very similar. They seem to have they have a difference in the part number 200SA and 000SA. And the only thing I can seem to notice is this one mentions OC for overclock, and the other one doesn't. So I'm sure these two are actually very similar, and maybe even just have the different firmware. But we can have a look a bit later and see what differences we can spot between these two cards. So, first thing we'll have to do with this is going to be to just take the heatsink off, get down to the PCB, and then let's have a look to see what we've got here. I'm just checking if it's warped. Yeah, slightly, but you know, it doesn't seem unusual with graphics cards these days, to be honest. But yeah, there does seem to be a slight warp in this PCB. Okay, let's take it apart. The first thing I notice is there's not much in the way of heatsink compound on the GPU itself. We can just see there. Doesn't look like it's popcorned or bubbled or burnt. That's a nice sign. I do see this deposit, and this is quite normal, so I wouldn't worry anything about that. This one I think is slightly different to Lewis's card. This has backlighting in the I think in the metal plate or somewhere. No, I think it's in the actual this Sapphire logo. It has a plug on here. Let's get the two cards together so we can actually make some direct comparisons. You know what, guys? These cards are the same. I think this is the actual part number of the PCB, and this one is the same. So what the difference is between the two, I don't know. Maybe it's just a different BIOS revision. Even this number here, B0119, B0119. So the first thing I need to do is to make a mark so I actually know which card is which, because when you're comparing two cards like this, it can be very easy to mix them up. So we'll put an L on here. This is Lewis's, yeah. We'll put a P on this one. Not really necessary, because obviously if there's a mark on one, we don't need one on the other one, but we'll do that. This is like contact lenses, by the way. I did wear them sometimes for leisure. These daily ones, yeah, they come in a pack, and you go to the optician and they kind of write L on one of the boxes, while you're there they write R on the other one. I kind of think, well, why? Because like, if the one that like has L on goes to your left eye, where do you think you're going to stick the other one? Why do you have to write R on it? Yeah, where the hell do you think you're actually going to put it? Apart from an L, of course. Anyway, little rant over. Strange things I notice, you know. So we can make some comparisons of the resistance readings on these. This one I know has a strange reading on 3.3 volts. So now let's compare this with the other one and let's see what differences we can find. I think the easiest way is for me probably just to draw it out roughly, or take a photo and print it so I know which which coil as well. I'll probably just draw it actually. So yeah, but the first thing I'm interested in doing is having a look to see what resistance on this 3.3 on the other card. This is the layout of the card. As I recall from the last time working on one of these, this was the PEX supply, 0.9 volts. This was the memory control. This was RAM. These were all core. This is all V core. And I think these were both filters on the 12 volts. I'm just checking. This was the 5 volt. I seem to recall that's how it actually was. And there's a 1.8 volt regulator somewhere. I couldn't quite figure out where it was. So that's what I think we have. Let's have a look on this one and measure some resistances and then just compare them with the other card. I have selected ohms range on the meter. Let's see what we've actually got here. So we go to ground. So this is the one that I'm pretty sure was PEX. So this is reading 25.5 ohms. You can make a note of that. 25.5. Let's go for the input voltage as well. So 12 volts coming in on the first three fingers. This is reading 5-6 kilo ohms. Yeah, somewhere in that region. Let's say 6k. So this is the 12 volt. Is 6k, and then the 3.3 volt is the fourth one coming in from the other end. 1, 2, 3, 4. So that's reading. Yeah, 211 ohms. I think is actually about correct for one of these. 211 ohms. This one, it'd be easiest to get to the inductor underneath, so we can have a look at this one. This I think is a memory controller, 26.7. This is the 5 volt. I'm pretty sure that the 12 volt comes into one end of this. So let's have a look. Yeah, 12 volt comes on this end of it, and then the other end of it I think is a reference, and this is the output. I'd have to check to be sure if that is the actual output. So either that one or this one. Okay, but they're both reading about 8k, so we can say that's about 8k. RAM is this one. So let's see what we've got here. Okay, RAM, yeah, 16.8. That seems a little bit low. Is it Samsung RAM? I'm not sure what the RAM actually is on this, without getting the microscope. But RAM is reading 16.8. and then the V core we should be able to read. Let's have a look. So it's on V core. Yeah, these are surface mounts to get onto one of the capacitors. 0.4. What's it reading on the short? 0. So that's reading 0.4. Let's meter zeros quite nicely. 0.4. Okay. 0.4 ohms. And then there's these two, which I think is possibly a filters on the 12 volt. I might even be able to check that actually. Let's have a look, see if we can get onto them. So we have this one here, 9.5k, and we have this one here. If I can just make a contact with it, it's a bit difficult. There, 9.5k, about the same. And I've got a feeling that one of these is connecting to 12 volts over here. Yeah, there. And the other one is connecting to the 12 volts coming up here. Whichever end of this is 12 volts coming in. I'm not sure which it's inside or outside. Okay, that one isn't. I thought that would have been. Ah, this is probably the filter. So this will be some sort of voltage rail, I think. It looks like this is the actual filter that's connected on the 12 volts coming in. This one, straight to ground. Well, that reads very low resistance to ground. Actually, that's not a good sign. This might have a shorted high side MOSFET. And does that go to 11 meg? No. I need to investigate that. That's reading very low on this one. That's this coil here. Is that reading the same from the fuses to ground as well? Yeah. Okay, so this card, this is Peter's card, has got, looks like a shorted high side MOSFET. And because it's reading down to about 0.4, the shorted MOSFET is on V core, for the simple reason that V core also reads about the same, 0.6, 0.5, 0.6, yeah, there you go. So that's what's wrong with this card. This has a short circuit high side MOSFET. Of that we can be sure, so we can have a look at that. And this one, as I say, is some sort of voltage rail. Okay, 9.5k. So the other coil is actually here, and this is where we have the two fuses. Are the fuses blown? That's a good question. I wouldn't be surprised. Yeah, the fuses have gone, look. Okay, and then this other fuse down here, this will be on the other 12 volts coming in, which isn't blown. So I think we can fairly reasonably say that this phase probably drives the memory controller and maybe the RAM. We can kind of work that out. If we go from the actual end of the fuse and we go to the junction between the two MOSFETs, we can find out which one the junction actually is. No, sorry, not the junction. If we go to the 12 volt coming in, so it doesn't go there. Oh, there's another MOSFET here. Top of this one. No, it doesn't go to the top of there. What about the one that drives the RAM? That's these MOSFETs under here. Are these powered from this 12 volt supply? Top of this one. Yeah, that one goes to there. So we know that 12 volt coming in is providing this. And I'm assuming the other 12 volt off one of these fuses is probably driving this one. Yeah, you can see it. You can see it. So 12 volts coming on here powers the main V core VRM, and it powers the memory controller. And the 12 volts coming in here powers this one. Okay, and we have a short circuit high side MOSFET. So we'll have to use one of our techniques we've used previously to trace which MOSFET. And they're not a MOSFET exactly on this. They're actually MOSFET drivers. You can see there, 1, 2, 3. Another one hidden under here, 1, 2, 3, 4, 5. So pretty sure one of these 5 is going to be short. Now let's have a look at the 3.3 on the other card. the one of Lewis's that has this 12 volts, 12 ohms on it. And let's see if we can figure that out now we know what it should be, where the low resistance actually is. This is Lewis's, Lewis and Albero. Let's have a look. So we know something about it now. We know 12 volt comes in here and powers the top end of this MOSFET here. That's powering this phase, okay? And we know that the 12 volt comes in here through the two fuses, which on this board obviously are okay, and that powers the main phase in here. Let's see what resistance we've got. So PEX is 42. Is actually higher on ours, which doesn't bode too well for the other cord, by the way. 42 ohms. The 5 volt is here, I think 1.4. This end I think is the end that comes in from the 12. Yeah, 1.5. So that actually reads different again on Lewis's card. 1.5. Okay, I'll put them in brackets, the ones on Lewis's. Memory controller, that's this one. What we got? Turn it over. Let's have a look. Ground. 34, 33. So they're reading different. Yeah, 33 ohms. This is an interesting one. The RAM that was reading 16.8 on the other one, and I thought that was low. Let's see what it is on this one. No, 19.2. That's within the realms of similarity. Ohms. Core. Is the core reading the same? What do you think, guys? Do you think the core will read 0.4 on this one as well, or will it be different, which would be a telltale sign? It's on the core. It actually reads the same on the core, basically. 0.4, 0.6. No, again, the other one's a bit lower. Yeah, 0.6. Peters. So it behaves differently. That's kind of like climbing up. It's not looking too good for this card, mate, I'll be honest with you. But let's carry on. Core 0.6. Lewis's. We know this is a filter on the power coming in. The one at the bottom, I don't think actually measured. Let's have a look. This is reading, yeah, about 6K. Just say it was a filter. Yeah, it's a filter on the 12 volts. So I think they read about the same. That reading is 6K on that one. And we can have a look. This is where you see the big difference. So on here, if we go from this inductor, which is the end of the fuse, this is reading, you know, 1.92K, yeah? And this one is reading short, okay? That's, you can see now the problem with this one. Last thing, this is the problem with Albero's card as far as I can tell. Albero and Lewis is the fourth one in. 1, 2, 3, 4. There's only reading 14 ohms on the 3.3 coming in, whereas on the other, I can't call it a good card, but on the other one it's much higher. Yeah, so we can see the difference. Right, let's have a look. So first of all, let's try and find which high side MOSFET or driver is short circuit on this one. I made a video recently, I'll link it to this one, how to trace short circuit high side MOSFET, and I looked at 10 different methods of doing this. I'm going to do this two ways, which will depend on the equipment you have available, but I'll use the ones I think are the most striking results. So the first thing we can say is that you will not find this short circuit with a multimeter. So if we go from the end of the fuse, which is connecting to the coil, if we go to the side of each coil, you will see 0 ohms. Okay, you cannot see which coil is short circuit, and that's because the coils themselves, the coils themselves read 0. They're very low resistance. So there is two fairly simple ways to do this that are very, very good examples of how to do it. They're very efficient ways to do it. Let's say that. Okay. So one of them first is to use an ESR meter, and I'll show you this way. And then if you don't have an ESR meter, I'll show you another way how to do it. So the way the ESR meter works, put it here where you can see it. Okay. Yeah. Is that if you have a short circuit high side MOSFET, then both sides of the coils are connected to ground via capacitors. The side on V core is connected to ground via these capacitors, and the side through the short circuit MOSFET is connected to ground via these capacitors, the input capacitors. And when you have capacitors on an ESR meter, it will basically read the ESR, it reads very low. So the capacitance will read practically 0. So now this is reading 1.16 with the meter lead shorted, okay? So that's effectively the resistance of the meter leads. So let's see if we can measure on this the difference between the coils. So that one's reading 1.25, okay? That's without it shorted. That's 1.25. What's this one reading? 1.18. This one, 1.25 again. This one, 1.25 again. This one, 1.23. So this one, 1.15. That reads the lowest. That suggests to me that this one is the one with the short circuit. Okay, so it's like the second one down from the square one. So that appears to be the faulty MOSFET. I'll just put a little bit of ink on a little mark. Okay, that one. So that was telling me that. Let's now try this using a millivolt meter and injecting some voltage into the circuit. So to understand this method, I'll just explain to you how it actually works. We have 12 volts coming in via these fuses, which is blown. This is where the short is, from here to the V core on the GPU. And the reason we have a short is that we have one of the phases of the power supply. So this has 5, 1, 2, 3, 4, 5 phases. One of these, which have these drivers, have a high side MOSFET internally that's short. So your basic buck regulator, your VRM, is like this. First MOSFET, second MOSFET to ground, go into your drive circuit, and coming from your pulse width modulator. So this sends pulses to this, and this alternately switches the two MOSFETs. So each time it gets a pulse, it switches one then the other. From here you have your coil, and this is going to your V core in our case, and this is your capacitors to ground. Okay. And this has capacitors to ground on the 12 volts. So that's what you have. And one of these is short circuit, but there's 5 and we don't know which one is. So one of them has a short. Okay. What I was just doing with the ESR meter, I was measuring from here to here. So on a good phase where this isn't short, this end of your ESR meter is connecting to ground through this capacitor because it's 100 kilohertz AC, it's not DC, so that acts like a short. And the other end is effectively just open circuit. It just goes to these two MOSFETs. So you're reading the resistance of the coil. On the one with the short, this end's going to ground via this capacitor, and this end is going to ground via this capacitor. And that's why I'm reading a lower reading. Sometimes you read 0 or practically. This wasn't very dramatic, but it did show a lower one. So that's that way. Now the other way I'm going to do is I'm going to inject in here a voltage, a low voltage 0.8 volts into here. Oh, somebody told me off actually. I'm going to apply a voltage to here, 0.8 volts, because you can't inject a voltage, you can only inject current, and I agree with him, whoever said that. So I'm going to apply 0.8 volts to here, which will inject current into the circuit, and the current will flow through the short circuit MOSFET, through the coil, into the V core, your GPU, and internally in your GPU it will go to ground. So the current path is that, okay? That's where the current is going to flow. Now that means that the current will flow through the coil, but it will only flow through the coil that has a short circuit high side MOSFET. All the other four, there will be no path. Okay, so if I measure the voltage drop across this coil, because when you pass current through any resistance, even a low resistance, you will get a voltage drop. So if I measure across each coil, all the ones that are not conducting any current should just read 0 millivolts, and this faulty one should give a reading. So let's get this set up and let's try it. To do this, I've tagged a wire onto the end of one of the fuses, because if I repair this I need to change these fuses anyway, not that it would actually cause a problem. I have the bench power supply on 0.8 volts, I'll turn the current up to full, so this can inject up to 5 amps into here. We'll connect the positive to this brown wire, okay, from the power supply, and then we'll connect the negative to ground. And I'll probably, no, I can reach, I thought I couldn't reach the wire. So negative to ground. Okay, and we're now injecting 1.6 amps, that's fine. So now let's take our millivolt meter and let's see if we can determine which inductor the current's actually flowing through. Okay, I have the meter there on millivolts. I'm going to get a mobile phone holder for this. I think I can just angle it a bit better, just get rid of the reflection from all the overhead lighting, but it's still clear to read. So we're on millivolts. We need to now measure across each of these coils and see if we have a voltage drop to say there is current flowing through that coil. So this is the first one. So that's reading 0.01. Okay. 0.01. 0.01. 0.47, and that's the one, the second one down, that the SR meter said it was, yeah? Just get a connection like, yeah. So that's the one. Okay. I actually also often use the little Aneng meter for this because it has a higher resolution. I'll just show you actually. It's one of the things I commented on the review of this. And by the way, those of you who watched the review, I had a reply from Kaiweets who said they'd watched the video, they were very interested, and they've now approached the R&D department to look at some of the things I raised, which would make this meter even better, or hopefully another, you know, when they bring the next model out. But anyway, this is this one. So this one reads down to 2 decimal places on millivolts, and this is not as clear to see, but it actually reads, if I just set it to manual range, and it reads to 3 decimal points. So this, which just tells the same thing, but it'll be a little bit more dramatic. So let's have a look on this one. This is the first one, yeah, 0.010, 010. Put the better meter probes on this one. 0.8. This is the one that we think is the bad one. Yeah, can you see it? Yeah. So we now know for definite where our short circuit high side MOSFET is. Just out of interest, by the way, it's not getting warm in any way. There's no heat here. In fact, if anything would warm up, it would be the GPU, because this is a higher resistance, about 0.6 of an ohm. So this won't warm up. If you want to get this to come hot, to find it that way, you need to connect your negative not to ground but to V core. So you're now injecting current between 12 volts, which is the short circuit high side MOSFET, and V core. You can now put whatever voltage you want in there up to 12 volts and get something hot. But I'm pretty sure you would agree that the two methods we use are very good, and one we're just using a multimeter on millivolts range. The other ESR meter, yeah, it's very nice, does the job. This is the short circuit driver, IR3553M. These are very common. I bought a pack of 10 of them for another repair, so I have 9 left. So let's get this changed, and then let's see whether the GPU actually survived the 12 volts coming in, given the fact that some of the other resistances are actually not what I expect compared with the other card. I've replaced the IR3553M, this one. It looks as well soldered as the other ones do, to be honest, so hopefully that's okay. I've also replaced both the fuses, so we can just check now. These fuses obviously now should just read like short, which they do. We can go from the fuse to 12 volt, that's fine, and from 12 volts now to ground we should no longer have a short. I'll just put the meter the right way around, so 12 volts to ground. Let's see what we've got. So our short circuit's gone away now. That's reading, well, 2.7, 2.8, 2.93k. We can compare that with the other one, just out of interest, but it should read about the same, so let's have a look. Yeah, it's reading about the same. So I think now we'll have to power this card up and have a look to see whether it's any good, if the GPU actually survived the 12 volts that would have come into it via the shorted MOSFET driver, and let's see what happens. I think the first thing we can just check on this basically is power it up and see if we have VCore. So I'll get onto VCore on the volts range. Power supplies on, ready to go. So let's just see what happens with this now. We have VCore. I'm not sure it likes it, but we have VCore. So we fixed the problem with the VRM, but it was making like a continuous bleep. Let's just disconnect the mining adapter we're using, and let's have a look to see, make sure the rig's working. It turns out that continuous bleeping was because the memory wanted resetting in the test rig. So we'll power it up again. I will just check on VCore, but it was running. And let's see if it actually works, this card now. So again, we have VCore. It's quite stable. Oh, what do we have? Hold on a second, guys. We have a blue light on the monitor. Yeah, and we have a picture. Let's see if this is working. Well, at least it's running in Windows. I'm just installing the drivers now, so we'll have to wait to see when the drivers are actually installed, whether it's working properly. But we can at least say that it does boot into Windows. I've installed Windows 10 on another of my test PCs because the one I've been using for some reason is running very slow. I'm not quite sure what's wrong with it. So I grabbed hold of the H110M that I got from the car boot the other week with the 7th generation i5 in it, and 16 gig of DDR4, and this actually is running much better. For example, the graphics card drivers took about 3.5 minutes to install, and that's not on an SSD, whereas on the other machine it took like 7 minutes. And then afterwards, although it was running with the drivers, once I tried to run any 3D program, Firmark, Unigine, it would just fail with these errors, these AMD errors coming up to say that there's some sort of timeout in the driver. It doesn't crash the PC. Sometimes it seems to lock up for 20 seconds and it just comes back again. So I'm not exactly sure what was going on. So anyway, I've installed the drivers on this other completely different machine with a different hard drive, and it's now running quite, as I would expect performance-wise. But I'm not sure this is working. It seems to be stable until you run some sort of 3D application, at least on the other machine. So let's just see whether or not this actually does run on this PC, or whether we get these errors. Okay. If we're still getting errors, then I suspect there's a problem with this graphics card, obviously, and whether this is because the 12 volts got into the VCore and didn't kill the GPU, but it's possibly kind of like a walking wounded, if that makes sense. The other thought maybe is that if I reflash the BIOS, I don't know the history of this card, I don't know why it failed, why one of the high side MOSFETs went short. But if it's not going to run properly now, I think it's worth trying to upgrade the BIOS or put a default BIOS in. And I might be able to do that actually with the graphics card, because it does basically run in Windows. Let's see what this does now, see if it actually runs or gives an error. Yeah, so I've got a black screen, as you can see. And then it comes back to here again, black screen again. And then does it come back? What's happening before it does come back? It just takes a little while, and then it kind of like wakes up. The blue light's still on the monitor, Yeah, see, so now it sort of comes back again. And then we get this, AMD software detected that a driver timeout had occurred on your system. So that's what it's basically doing. Let me just try FireMark as well, and that I think just locks up. I've restarted the PC, and actually there's a BIOS switch on this, so I switched it to the other BIOS, which is like towards the front of the PC, away from the ports, which I believe actually is the higher frequency BIOS. But let's just see what it does on that one. So we can again we can run the Heaven benchmark, I think. See what it does. Okay. Well, actually, it opened quicker. Whether or not that's actually going to tell us anything, I don't know. But it's loading. It seems to be when it starts that the thing actually crashes. Oh. Yeah. Okay. So we got some flicking little, a little bit of pixels on the screen there, and artifacts, and then it stopped. So maybe this is something to do with the BIOS. I'll see if I can find an official original BIOS and reprogram this card and see if it actually then wants to work. I've tried flashing the default BIOS, if you like, the reference one. I have two BIOSes. One says it's actually the wrong one, and the other one says that's the one that's already installed. But it doesn't seem to have helped any with this. If we just go to FireMark as a good example, the machine's stable, say, until you try to run some 3D application. Let's just go to the stress test, and you'll see it runs for an instance, and then that's it. Then it just locks up basically, and then it's kind of locked the machine up. If you give it so many seconds, it will sort of come back or just shut down and stop on its own. Just give it a moment. Just stop that flashing. That just stopped flashing. I don't know why it does that. Yeah, so yeah, there it goes blank on its own, and then after so many seconds it comes back. I think what actually happens is I think it finishes the benchmark. Yeah, it times out. So there you go. So you can see what's happening. I mean, it's the GPU loader's there. It's running basically, and then we get this timeout, driver timeout occurred. So that's what the thing's actually doing, and it just appears to me to be crashing once the GPUs run under load, which I suspect is caused by the fact that too much voltage got into the GPU. I'm not sure that I can really get much further with this one. So this is the video that I made using the second one of these RX480s, and I have it on one side waiting for a buck controller, but I wasn't convinced in the video that was actually faulty. I felt something else was probably causing the problem. You can watch this video, you can see it all in detail, and I don't have any schematics or board views. And this guy came on, Justin C, and he mentioned that I removed this chip U200. He gave me the part number of the chip here. He says it's responsible for fan control and some other communication. He says, I found two shorted until now on two different cards. The 3.3 volt line was almost shorted to ground, 10 to 20 ohms. Sounds like what I have. Once replaced, he had correct voltages. Okay, then he says there was other problems. So he's suggesting that that chip may be causing the problem. So what I can do here is, first of all, just remove it and see if it runs without it, and if it powers up or not. Otherwise, I could try to replace this chip and see if the problem actually goes away. So this is the actual chip, this one here, near the back of the card, or the front, whichever way you want to look at it. And this is the one which he suggested I have a look at removing, which is U200. I'll just zoom down on the overhead camera, see if that's good enough. Otherwise, we can use the microscope to look at this. This is the chip then under the microscope, and I'll just show you the data sheet for this. But basically this pin 8 is the power pin for this chip. Here's the data sheet. So it's a monostable multivibrator. It effectively puts a delay on the pulse, or rather makes a pulse a certain width. That's the best way to describe this. So that's our chip, and we can see VCC is pin 8. And this is where he thinks the low resistance will be. So let's have a look. This is the graphics card which we were just looking at, the one that just crashes, basically. We can just get onto ground on this one, and we can go to the pin 8 on the chip. And you can see it reads 210 ohms. That's the supply to the chip, 210 ohms. Now let's have a look on the one which Lewis and Albert gave me, the one I was waiting for apart. It's lower down, so I'm sure I'll have to just adjust the focus on this one so we can see it. Okay, there we are. So that's the chip, yeah. And again, we can go to ground and look at the resistance on this one. And it reads about 14 ohms. So this is basically the same resistance. I'll get onto it. Why has it changed? It's just changed for some reason. Guys, you just saw it. Yeah. That's unbelievable, but you actually saw that reading 14 ohms, I'm sure you did. Yeah, 14 ohms. When I push down on it, that's... push again. Now it reads similar to the other one. This is very strange. That pushing down on here changes the reading. I wonder if we have a... yeah, 14 ohms, look. So you go to this capacitor. Yeah, it does. That's ground. I think either this capacitor's got a problem or this chip's got a problem, but that's a very strange thing. Yeah, 14 ohms. Let's push on the capacitor a little bit. Now let's try it. 14. Let's push on the chip a little bit. Then let's try it. Okay, now I can't get it to change. Let's just go to the same point as well. Let's have a look. This is a resistor. Go to the same point. This, I'm assuming, depends if it's a low value resistor. Yeah, 51. Is that kilobytes? Yeah, okay. So it can't be the resistor that's doing it. 14 ohms. Let me just again give it a little push. 14 ohms. So now it's steady at 14 ohms. I really find this hard to understand why that was changing. 3.11. I'm tempted maybe to remove the capacitor, and if the problem still occurs, to remove the chip. I'll need to switch it off one moment. There we go. Back to ohms range. Okay, there we go, ohms range. One more time, because this is just a strange thing to find. 14 ohms. Okay, let's take the capacitor off. If that makes no difference, let's take this chip off. And then let's see if it actually will run without it, or at least power up without it. I'm interested to see, otherwise I need to order parts for this. But this obviously does seem to be where the issue actually is. I've just flexed it slightly. I'll be interested to see if I can get the fault to go away again. Okay. No, now it seems to be steady. Okay, let's see what's causing the problem. I've removed the chip and we can have a look now. So this is where the short effectively was. Well, low resistance. It's still there. And I'd say basically I'm just reading the resistance on the 3.3 volt rail. So from here, I'm sure it just goes back to 3.3 volts on the power coming in, yeah, on the PCIe connection. So that's all I'm really doing. I'm just trying to think if there's some way I can figure out where this low resistance is. Although in fairness, the 3.3 volts was present. even with this low resistance, it doesn't draw that much current that it would actually cause a problem. I think I worked out about 300 milliamps or something it's drawing. I really need a schematic or a board view for this so I can figure out where this voltage rail goes to. But what was a little bit strange was the fact that I could actually get it to go away by pushing on here. You saw it yourself. So I'm wondering if it's just possible this capacitor is actually the problem. So let's remove the capacitor as well for the hell of it, and let's see if we still have the same problem. I've replaced the original one. I did actually try it. I did actually try to power it up without this fitted just to see if it would make any difference, and it didn't make any difference. It still basically hangs up in the power sequence. It only gets as far as PEX. So this once again is waiting for the ports it was originally waiting for, but that should be here fairly soon now, and then we can get further into this to see if that IC actually solves the problem with the 0.9 volt power gauge going high and low. If it doesn't, then we just need to trace this further without a board view, unfortunately, and see if we can figure out why. There are a couple of other ideas I have with this to see why it's unstable once it runs any 3D. One of the thoughts I have is, are all of the phases running on the V-core? Because I had to change that shorted driver, I guess it's within the realms of possibility. It's damaged the PWM controller, so it's not getting any drive on that channel. And maybe if this is running, well, I say channel, I mean phase. And maybe if this is running on 4 phases, it should explain the instability once you try to make it do any real work. So that's one thing I'd like to check out. So let's see if we can work out whether or not that is actually the case. I'll have to dismantle it again to do this. Because I think, well, I obviously need to get to the PWM controller. And the driver, so I can see, I'll use the oscilloscope and then maybe the multimeter on hertz range as well to see if we can determine whether they're all actually running. This is the data sheet for the MOSFET drivers on each phase, and you can see that switch, this terminal, which is all the pins on this end, this goes to the coil and therefore to the V out, V core in our case. And we have pulse width modulation coming in, PWM, on this pin, which is pin 19, it says. So it's on the opposite end from a switch, and it's the third one in from this end. So we can check the resistance on PWM to ground on all of them just to see they should be the same. And then we can use an oscilloscope and we can have a loop to see if we have drive getting to them all. And I'm also inclined to see if we can see anything happening on switch as well. Because it's this side of the coil, you'd expect to see effectively pulses on here, and obviously the other side is smooth DC. So let's have a look to see what we can find on ours and see if we can determine if they are all actually working. We can make some resistance checks first, so let's have a look. This is the first one, so effectively it's from this end, it's the third pin in. So there's 7, 1, 2, 3, 4, 5, 6, 7, yeah, okay, so it's this one. So that's reading 4.848. What's this one reading? 1, 2, 3. This is the one I changed. Let's have a look. Let's get the connection on it. Yeah, 4.910. So it's very close. Let's have a look at the other ones. This is the third one. 1, 2, 3. Oh, that one reads a bit higher. No, 4.82. Let's go again on the next one. 1, 2, 1, 2, 3, 4. It's easy to count from this end. It's this one. Let's go on to ground. Oh, that one reads completely different. Let me just check again. 1, 2, 3. Oh, this one reads really different from the other ones. That's interesting. Let's make sure I've got a good connection to ground. No, it's the same. It's just a bad connection to ground. 4.79, and then the last one is down here. 1, 2, 3. 4.83. So they're all basically similar. I mean, there's slight differences, but nothing that stands out to say is a problem. So let's have a look to see if we've actually got a signal on there with the oscilloscope on the PWM pin. I have the oscilloscope set up where you can see it. So I'm actually just going to go onto the end of the inductor here, which is connected to the switch terminal here. It's just the easiest place to get to it. So this is the first phase. Now let's see what we can see. Yeah, so can you see there's like a voltage level with some pulses on it. I'll just switch it off again. Yeah, don't want to get too hot. That's the first one. This is the one that I replaced, and that what you see that isn't running. Can you see it? It's just like a voltage level. Go to the next one down. This is the third and fourth ones for comparison. So number 3, and again you can see like 2 lines if you like. Okay, just switch it off again, and we can go to the fourth one. But I think we can conclusively say that the one that I replaced isn't actually running. Let's switch that one off, and then we can just go to the last one down here. Okay, so yeah, again you can see it. I think if I put the oscilloscope onto AC rather than DC and turn the sensitivity up, you'll be able to see it better. So let's go on to AC. I'll just move us up to the middle somewhere. Let's turn the sensitivity up. And now let's see if we can see it more clearly. So I'm back onto the first one up here again. Let's see what we've got. Yeah, you can see it there quite clearly. If I just there, yeah, okay, you can see them. So that one's definitely running. What's this one showing? This is the one that I fit the new driver. Put the switch back on the motherboard. It fell off the on-off switch. Just one moment. Okay, it's on. Right, let's start it. You see, so it just jumps and then it goes flat. So we definitely have one phase here not running. Again, we can go to the third one, which will be like the first one. Again, we can switch on again. Yeah, you can see it's running. So I think that's probably the cause of our instability, the fact we have one phase not running. It's the one I actually changed the chip on. So what I need to do now is have a look under the oscilloscope to see if I see the PWM pin has any drive on that one. I'll compare it with the first one. We can see then that one of the phases isn't actually running, which happens to be the one that I changed, this one. We can make a couple other checks with this actually, just to first of all to see if we have any drive getting to it from the pulse width modulator controller, and secondly, if you look at the datasheet for these chips, I'll just go back over to the Windows desktop one moment. Let's take another look at the datasheet for the IR3553. This is the MOSFET driver and integrated MOSFETs basically. We can see, if I just look at the block diagram, yes, this one. We have PWM, pulse width modulation, coming in. So this is driving the phase coming from the multi-phase pulse width modulator controller quite clearly. And we also have this pin, there's 2 together actually, gate L. Now gate L is connected internally to the driver for the low side MOSFET. And if we look at the data sheet, we'll see it. So gate L, low side MOSFET driver pin that can be connected to a test point in order to observe the waveform. So we can use that as another method to see if this phase is running, although we know it isn't really from what I was measuring on the coil itself. And the other pin, pulse width modulation, this is the drive coming in from the pulse width modulator, as I just described. We can see where the pins are. So we have gate L, this is the dot pin 1, so the 5th one down this side, the last one in fact, is gate L. So we can measure the waveform here to double check to see if this phase is actually running or not. And the 3rd one in from this end, PWM, we can check the pin here to see if it has any drive or not. We can now again compare a good phase with a bad phase. So I'm going to look at the gate L pin, which basically confirms what we could see here, I would say. that this one isn't running. Now we could get the pulse width modulation pin coming in, which is the drive coming into the chip, to see if they both have drive or whether the short in this damage the driver. So we can have a look. I'll just get onto the gate L pin, one moment on this phase. Okay, so I'm on that pin. I don't think this pin actually goes anywhere, it's just effectively a reference point for a test point if you like. So we can switch this on and let's just run it. Okay, it's running. You can see that it's running. Let's have a look at the pulse width modulation pin coming in. Well, in fact, we know this will be running because the output's running, but we can have a look, see what it looks like. Just be very careful to get onto it. There we go. Again, we can slipped off it, one moment. Okay, we're on it. So again, we can switch on and let's have a look to see what we have here. And again, it's running, so we can see that as running. Now let's have a look at the bad one. So this is the bad phase. So again, we can go to gate L, which we should be able to see the waveform, although I suspect there's nothing here because there's nothing on the coil. So we're on gate L. Yeah, and we have nothing there on that one basically. So that isn't running. So is it because this thing isn't working or not soldered down properly, or is it because it's got no drive? So let's have a look. That's pin 90, which is the third one along here. So this is a drive coming in from the pulse width modulator chip. So again, we can have a look at this. Let's see what we've got. And we have nothing. So we know for sure that the problem is that this chip has no drive. Well, let's have a look to see if that goes directly to the pulse width modulator chip over here. This is the pulse width modulator controller. We need to have a look at the datasheet for this one now and figure out how this drives these phases here. Is it going directly? Is it going through resistors or something similar to that? So the part number for this, I've actually looked up under the microscope and I'll just show you what the datasheet looks like. This is the datasheet. It's an IR3567B. It's a 6+2 phase pulse width modulator controller, and I think I was just running with 5 phases plus 2. That's quite normal with these, that you can run them, you know, with less phases than the maximum it can drive. If we have a look at the pinout, the only thing we're really interested in are the actual outputs. So we have 6 pulse width modulation outputs here, 1 to 6, and we have pulse width modulator for effectively for number 2, output 2, L1, L2. So this is just 6 phases, and this is your 2 phases, which now I'm pretty sure is actually driving the memory controller. But again, that's not really relative to what we want to work out at the moment. We're interested in these 6 pins here, and we want to know how they connect to the drivers for each phase. We can check this quite easily actually. I'm on continuity. So if we go to each of the phases, pretty sure I can get onto the pin 3 down here, and let's see if it goes to here. Maybe I'm not on the pin. I might have to use the microscope. Let's have a look, see if I can just do it. One more go, and then maybe I need to use the microscope to get onto here. Oh yeah, I've got it. So that goes to one of the 6 pins. The next one here, yeah, goes to here. That's the phase that isn't working, by the way. That's probably all we need to check. We know the other phases are working anyway, and we know to go to the chip. So we know that the pulse width modulation input here comes directly from this chip. It's not via a resistor or anything else. So we can say with certainty really that the problem is this. Therefore, it appears my hunch was correct, that the reason for the instability once we began any sort of 3D processing was the fact that we have one phase in the VRM not running. Yeah, I'm pleased actually with that that diagnosis and the way that I came to that. Let's have a look to see if we can find these chips on AliExpress. I don't have them in stock. I've had a look. I thought I may have had this one, but I don't. But again, it looks like one that's probably worth keeping in stock. I'll probably find this more often. 3567B. Yeah, so we can get these in packs of 5. How much they are? This seller, SUHMS, I use them quite often. They seem to be rather good. So, yeah, they're a little bit expensive. But you're talking sort of like €4 each. Yeah. I'll just check with Michael, who owns this card, if he would like me to order parts for this. I can't 100% guarantee it will fix it, because it's still possible there's damage to the GPU. But I think it's a very good possibility this will fix it. So, Michael, let me know on this if you don't mind paying for the parts, and then I will order them. And it will take, well, it's saying delivery June the 7th, so it'll take a little while to get here. There we have it, guys. I think that was quite interesting. Hope you guys thought it was interesting. I haven't particularly explored this type of fault before, where I have cards that are just crashing like this one was doing. I have at least one more here, a subscriber's card, that's doing the same thing. That I'll just let you know, because you're probably watching whose it is. One moment. Yes, it's this one. This is Mark's card from the UK, RX5500. I've started repairing, I've started a video on this, and I got as far as where it was doing what this one is doing, which is just locking up on Firmark or on Unity in Heaven, and basically the same way this is doing. So that now gives me another opportunity to look at this to see if I can figure out, is it the same sort of problem. And in fact, the video, this one, I think maybe I hope that quite a few of you guys have now learned another method to try and diagnose some of these faults that we find on graphics cards. These annoying ones I call like not really a fault. But in this case, yeah, maybe it probably is actually, and we can trace the electronics and say that's what's wrong with it. Okay, so I have to wait for a chip. Take a little while, but we know there's no components in between. We know there's no drive coming out of this, so I'd have to say we can be very, very sure that will fix this problem, and hopefully it will fix the instability in this one, can go back to the owner. Okay, see you all soon on another electronics repair video. Soon, guys. Ciao for now.